Well then, first, welcome to a Biosecurity, a technical perspective. So this talk is presented to you by Jasper and Mona. Jasper is freshly graduated from the Institute of Virology of the Hanover Medical School. He wrote his thesis on virology. Now he is working on biosecurity road mapping for the convergence. And Mona studied medicine at the University of Würzburg, and now she works for Alvea as a clinical trial physician. Now, before we start with the presentation, please, I would like to remind you that you can ask questions on swap cards by going to the session, clicking on live chat, and then you've got a tab where you can ask the questions. So feel free to do so during the presentation. Thank you. And a round of applause, please, for Jasper and Mona.
Okay. Hello, everyone. Thanks for the intro, Theo. Can everyone hear me also in the back? And please, tell me as soon as you stop hearing me. Yeah, we're really excited to be here today to talk about biosecurity from a technical perspective. Someone just asked me if we are also going to talk about COVID, and obviously we're going to talk about COVID. I'm sorry about this. I think we're all sick about hearing about this. But while preparing this talk, we talked about how we failed during this current pandemic, and we came up that most failures were actually from governance issues. However, if we look into the past, just decades ago, this was quite different. For most of us here, the COVID pandemic is the first big pandemic that we can remember living through. So it might not be as obvious to us that how much technical advances have changed our pandemic preparedness. For the longest time in human history, we have been basically at the mercy of infectious diseases without rapid testing, personal protective equipment, or rapid vaccines. But despite all of our technical advances, we are still not prepared for the worst possible outcomes. COVID has been really, really bad, but it is important to keep in mind that the next pandemic could potentially be even worse. Okay, so let's quickly recap why a lot of people in EA care about biosecurity and why we should care. So first of all, pandemics can be devastating. We have a long history of recorded pandemics, starting with the Black Death in the 1300s, which caused up to 200 million deaths in Asia and Europe. It is the most fatal pandemic ever recorded in history. Yeah. The second reason is biological risks are most likely increasing. We've had a lot of technological advances over the past couple of decades, here exemplified on the left by AlphaFold. AlphaFold enables scientists to translate huge databases of sequence information into workable structure data. And in addition, costs for technologies are also rapidly falling, which constantly lowers the bar for access to potentially dangerous technologies. And then we would hope that people who are smart enough to use these technologies are also good people and would not want to misuse those technologies. But thinking like this would be naive and historically has already been proven wrong. Here we can see the leader of Aum Shinrikyo, which was a Japanese doomsday cult. They tried to commit mass murder by engineering weaponized anthrax. They collaborated with a microbiologist, and eventually those efforts failed. And so they resorted to poison attacks in the Tokyo subway. But as biotech becomes more and more accessible, omnicidal actors will eventually be able to successfully engineer pandemics. And yeah, the third argument is that biological risks are neglected. Here we see the American Pandemic Preparedness Plan, as it was suggested by the White House. We can see that significant sums of money are allocated to various interventions, And then on the right, we see the PREVENT plan, which is the plan that was actually ratified by Congress. And you can see that most of the interventions didn't get allocated any resources, and overall there's a lot less resources allocated to pandemic preparedness.
Yeah, and you might object and say, well, biosecurity is not neglected. This is an established academic field. There are people working on this. So we first need to clarify a couple of things. So first, the EA biosecurity community practices what we like to call scope-sensitive biosecurity, and thus focusing on unlikely but really devastating tail risk events. This entails global catastrophic biological risks, or GCBRs for short, and their subset of potentially existential risks which threaten the continuation of humanity. We will probably use the term GCBRs a lot, or at least a couple of times, so a quick definition. The Nuclear Threat Initiative defines GCBRs as biological risks which have the potential to undermine humanity's long-term potential. And secondly, the scope-sensitive biosecurity focuses primarily on engineered and deliberate releases. This follows from the tail risks focus of scope-sensitive biosecurity. And even though natural pandemics have so far amassed a greater death toll, for example, the Black Death, compared to engineered pandemics, of course, we have reasons to believe that natural pandemics are not really a GCBR or an existential threat, but engineered pandemics definitely are. The reason is that natural pandemics are usually subjected to evolutionary trade-offs. There's the optimal virulence hypothesis, which says that, which claims that the virulence or lethality of a pathogen and the transmissibility are being traded off, since a very lethal pathogen has a hard time to spread among the population. And this is not necessarily completely true, but natural pathogens have a lot of just evolutionary trade-offs, whereas with biotechnology and engineering, we can surpass these trade-offs. And thus, accidental releases of engineered pathogens can be very dangerous, but the deliberate releases which combine this human-centered design, the potential to surpass these trade-offs, and malicious intent, those are the scenarios we really care about and we are really worried about. And when we say biosecurity is neglected, we actually mean this scope-sensitive biosecurity, not the zoonosis, One Health focused established biosecurity. And this makes a difference because some of the interventions we knew from the COVID pandemic, such as contact tracing or rapid testing, which worked great there, they might not do much in a GCBR scenario where we actually threatened with human extinction. That being said, how can technology help us mitigate such scenarios and defend against GCBRs?
All right. So first of all, let's look at when we can intervene in the course of a pandemic. This graph shows the course of a pandemic, time since outbreak, and the damage it causes. So broadly, we can split the interventions into 3 buckets. The first being prevention, then detection, and then response. Obviously, preventing a pathogen from arising would be the most convenient, but we cannot be certain that our preventative measures actually work. Therefore, we also need to spend time and effort on the other 2 interventions. Then detection, the earlier on we detect a new pathogen arising, the sooner we can intervene and considerably shape the course of a pandemic. And finally, response. These are all the technical interventions that we can use to mitigate the pandemic and stop it from becoming a catastrophic biological risk or even cause extinction. All right, now it's your turn. We want to spend 3 minutes. Everyone, please grab your partner and talk about any sort of technological interventions that you might have heard about. And obviously, we don't expect you to be experts on this, but everyone here has had 2 years of first-hand experience of a pandemic, so you probably know a lot more than you think. So Jasper, can you set the timer and we'll meet again in 3 minutes. All right, everyone. All right. Thanks so much, everyone. I think you probably came up with a lot of very interesting interventions, and let's go into a bit more depth for some of those. Starting with prevention. So for prevention, we actually see the most significant opportunities in governance, and Tessa already talked about this in depth this morning in her talk. So we won't focus too much on this. Interventions could be like promoting responsible science, regulating dual use, and access to sensitive data. One aspect that is actually enabled by technical solutions is deterrence. The better our detection and response capabilities are, the higher are the costs for actors to misuse bioweapons. And of course, there are also technical information security aspects that are deeply entwined with governance questions. And here I want to mention one example of the Secure DNA project at the Sculpting Evolution group at MIT. The Secure DNA project aims to screen and block all DNA synthesis orders containing known hazardous or suspicious sequences. So for example, if you tried to order parts of the smallpox genome, this would flag it and prevent you from getting it. And eventually, this is supposed to not just cover the major commercial DNA synthesis provider, but to be locally run on any DNA synthesis machine in any lab.
The detection bucket might seem simpler since it just includes any technology which enables us to robustly and rapidly detect a novel outbreak, but this might just be deceptively so. Because early detection, especially rapid and robust early detection, is pretty complicated. It usually includes metagenomic sequencing, so any sequencing technologies which sequence all of the DNA and RNA which are present in a sample. This can be a clinical sample in the case of clinical metagenomic sequencing, where we might sequence randomly sampled patients or patients with suspicious symptoms coming to a hospital with the hopes of catching a novel pathogen as early as possible. Another approach would be wastewater surveillance, which was also successfully employed during the COVID pandemic, although in a targeted manner, so specific for COVID. And wastewater monitoring, especially metagenomic wastewater monitoring, cast the detection net even wider by sequencing all of the DNA and RNA in wastewater to catch unknown pathogens or novel outbreaks even quicker. But also digital pathogen surveillance technologies which integrate all of these data streams, be it genomic information, public health data, travel information, so on and so forth, into a singular data stream which enables us to track pathogen spread. And one halo project within the EA Biosecurity community is the Nucleic Acid Observatory, or NAO for short. The NAO aims to sample water, either wastewater from critical infrastructure like hospitals or airports, as well as water from, say, river outlets or water reservoirs, and sample water from these locations to catch pathogens, unknown pathogens, known pathogens for causing novel outbreaks as early as possible. And the NAO aims to perform large-scale metagenomic sequencing, filtering the water, extracting the DNA, RNA, doing either unbiased amplification, so just anything in there, or targeted amplification for known pathogens, and then detect and characterize all the genetic information in the wastewater or water sample. And the NAO ideally sounds alarms, either when a certain sequence which is unknown is, for example, exponentially proliferating, indicating some sort of spread, rapid spread, or if a known hazard is detected, or if we find some markers of genetic engineering in a pathogen genome.
Okay, and lastly, we have response technologies, which are all the technologies that help us contain and mitigate and potentially survive a pandemic. And this can be anything from passive improvements to our built environment, like improving air filtration or sterilizing surfaces by UVC light. Another big important aspect is personal protective equipment, or PPE for short. Personal protective equipment is essential in a pandemic setting so that essential workers can still go to work and continue building vaccines or keep the power grid running. And then we also need medical countermeasures, so this can be everything from vaccines to antiviral medication. And I want to spend some more time on this last aspect of medical countermeasures and specifically vaccines. So one example here is Alvea. This is the company I've been working for a few months. Vaccines have been critical in the current COVID pandemic. We got vaccines in less than 1 year, which has been an incredible and never before seen achievement of science. However, 9 months in a pandemic setting is still a long time. And in addition, although here it seems like everyone who wants a vaccine has gotten vaccines, including booster doses. However, this is not the case for low middle income countries, where only about 22% of the population have received 1 or more shots. So Alvea got started in January this year as Omicron was just emerging and getting more and more relevant. And we started tackling some of the underlying challenges of vaccine development by developing our own vaccine, specifically targeting the Omicron strain. So you might ask, what is the relevance of this? We already have so many vaccines out there, so why do we need another one? Let's take a moment to think about if you wanted to build the perfect vaccine for any sort of disease. Which properties should it have? So first, every vaccine should be safe, so people should not be afraid to get the vaccine. It should be effective, it should prevent people from getting the disease, spreading the disease. Scalability is a very important factor in the pandemic setting because when we have a pandemic, we need to be able to rapidly upscale manufacturing production capacities. It should be affordable. This might not be a huge factor for us here or most of the Western countries, but it is an important aspect in low middle income countries to get more people to actually be able to receive the vaccine. A vaccine should be stable at room temperature, so it can be stored in ambient temperatures, which would make shipment to low middle income countries easier as well. And finally, we need to be able to be faster producing vaccines and then also be able to adapt it to new arising strains, variant new viruses. So Alvea has its founding roots in the EA movement, and therefore we care more about the potential positive impact that we can have than maximizing our revenue. And therefore our approach differs quite a bit from the typical pharmaceutical company. And our focus is specifically on reducing vaccine inequity and mitigating the risk of future global health threats. On this slide, you can see the first vaccine we built, which is based on DNA. DNA, like mRNA, has the advantage that it can be easily adapted to new strains and variants. DNA has some advantages over mRNA. It is more stable and therefore doesn't need to be frozen at very low temperatures, which facilitates shipping to especially like rural countries, rural areas. And yeah, it also, the stability aspect also facilitates a simpler design of the vaccine. So our vaccine is just comprised of plasmid DNA and a buffer solution. Some more numbers about Alvea. So we got started about 8 months ago. By now we are over 40 people from a diverse set of backgrounds. Yeah, we started dosing the first patient in a phase 1 trial in South Africa 5 months after first thinking about this idea. And by now we have enrolled 130 patients. We are funded from a variety of EA-aligned funding organizations. So this is just one example for a medical countermeasures company. And obviously most medical countermeasures are run by non-EA organizations. But I think this is a good example to show that EA can contribute a lot because we might have different values, different approaches. And by aiming high and being really ambitious, we can accomplish a lot.
Yeah, so you got a good overlook of possible and existing and future and promising technical interventions in biosecurity from information security aspects, metagenomic surveillance systems in clinic or in wastewater, PPE, medical countermeasures, built environment improvements. So where do we see project gaps in here? This is honestly not as obvious and not as clear to answer. There are currently a lot of prioritization and road mapping efforts being started, most of them too early stage to share. And there will be much more clarity within and between those intervention buckets in the future. But very broadly, if we think about just roughly where challenges are in those areas, in those fields, early detection is just very complicated. There are a lot of open questions, there are a lot of uncertainties, how it will work, how it will actually look like. So this is an area where we'll still need a lot of research. Just basic assumptions need to be checked before we can actually build a robust and rapid early warning system. But being faced with uncertainties and downside risks and info hazards, as biosecurity sometimes is, working on PPE is just always robustly positive. We will need great and cheap and super good PPE and GCBR scenarios, and work on PPE rarely can go wrong. So this is always a great area to work on. You now hopefully saw that biosecurity is a promising field. You got some good governance interventions this morning. You now saw that it's kind of tractable. You saw that the scope-sensitive biosecurity is neglected. And there's a lot of work to be done in the space. So the last question for many of you might now be, what can I personally do? And the first question might be, should I get involved in the first place? Because personal fit matters in biosecurity. Some desirable qualities include discretion. It's an area with info hazards, existing stakeholders, sensibilities, also downsides, so you need awareness for downside risks. Many technologies and approaches are either dual use, so meaning can be used for positive and negative ends, as well as you have unknown or undesirable second order effects. And lastly, this scope sensitivity, which I mentioned in the beginning, the prioritization of worst case scenarios which are not covered by the established biosecurity field. At the same time, it's a very exciting interdisciplinary field where there's a lot to do and you don't need a deep technical bio knowledge to contribute. Generalists can do a lot. There are, of course, questions where you actually need deep bio expertise. But there's plenty of work and plenty of research to be done for, say, material scientists, clinical trial design people, cybersecurity folks, and so on and so forth. So that's great. And that brings us to our second short interactive break, where you can think to yourself, or also, again, talk to your neighbor about why or why not it would make sense for you to work on biosecurity. And if you're fully new to this, what are your uncertainties about this and how you might answer these uncertainties? So, 2 minutes. All right, everybody. Okay. I know there's a lot of uncertainties you can work through, but yeah, we will have time for questions and office hours later. Okay, yeah. So what are some career capital gains or personal fit tests you can do? Some of them you probably already know. To gain long-term biosecurity experience or do fit tests there, you can join one of the many existential risk fellowships, SERI, CARI, CHERI. You can try to work or intern at places like the Center for Health Security, the Sculpting Evolution Lab, Nuclear Threat Initiative, the Future of Humanity Institute, the Center for the Study of Existential Risk, so on and so forth. You can find out about biosecurity projects in the community, try to collaborate on them, and just talk and network at EAGs. That's always great. You can also, of course, build general career capital, which might include doing a PhD in a relevant technical field, work at relevant government departments or international organizations such as the WHO, skilling up in fields like public health, epidemiology, so on and so forth, or just get much needed management experience. Just to go very briefly over this, there are a bunch of resources and organizations you can check out if you want to read up on this. There are pretty good reading lists and project idea lists in the EA forum, all collected under the biosecurity tag. There are also publications from places like the Future of Humanity Institute, the Nuclear Threat Initiative, or the Center for Health Security. They are all great, and you should check them out if you're interested in this. And the last important note, there's not a ton of mentorship, so it's important to show initiative, network, read up, approach people with your ideas, but don't rush ahead and take unilateral action, because there are actual downsides connected to many of the work in EA Biosecurity. You can, of course, contact us either by email if your email program supports emoji. Also my normal email and swap card. We have an office hour later. We will also have a biosecurity meetup later this evening where Tessa and Anemone will also be. So there's a chance to speak more to us and other people who are interested in biosecurity. And with that, we are ready to answer your questions. And just because Tessa just very poetically ended her talk with the solar punk future we want to see and thus prevent existential risks, to see like biotechnology in check, helping us to achieve the glorious future we want to live in. I'll leave you with this nice picture under which we will have our Q&A now. Thank you very much.
Yes, thank you very much, Jasper and Anemone. So we're about to start the Q&A. So again, feel free to go on the app, the Swapcard app. You can take a look at the questions, upvote them, and in the meanwhile, we're going to set up the scene. All right, then let's take a look at the questions. So, okay, this one. So, what is done currently to prevent possibly dangerous gain-of-function research?
So there are some approaches which aim to just do cultural change in the life science community. And being recently dropped out of the life science community, I'm not super in touch with those. But it is still a problem, since many of the life scientists don't really think about the downside risks a lot. And again, from the earlier talk, Tessa had the example that one of the PhD students she talked to had heard more about how to hang up your lab coats so you won't trip over it, rather than just talk about the downsides of viral engineering and so on. And this is still a problem. So what we ideally would like to see is that grant makers as well have a very explicit role and explicit goal of not funding research with very strong downside risks. And there were discussions about this when some of the bigger dual use and gain of function experiments were done. For example, the airborne influenza H5N1 or the monkeypox, not monkeypox, the mousepox vaccine evasion experiments. But they thus far haven't really led to a deep cultural change in the community. And some debate for sure, but so far grant makers and so on haven't really picked up on this universally.
Right, and would you say that it's for those gain-of-function research that are pretty risky? Do you think that it would be just good to just not do them at all?
Yes.
Thank you. I asked this question because it's not obvious to some.
Yeah. I mean, usually it's being argued that, you get some benefit out of this. You learn some biological information.
I know that theory, yes.
Yeah. The track record isn't just great, and a lot of things you can also do by doing loss of function research. You might have to get creative, but it's not impossible to get relevant knowledge without doing dangerous gain-of-function research.
What technology would you be most excited for the Berlin-based WHO Pandemic Intelligence Center to focus on?
Shall I? Okay. I would be pretty excited if they would really dig more into wastewater metagenomics. So far, the NAO at the Kevin Asfeld lab is the only place, I think, which really works on the actual implementations and algorithms of how such a system would look like. And there is a lot of metagenomic sequencing experience just in academia, and people have done a lot of environmental metagenomics, and they really know the area, but so far there isn't really one place, one big agency which pushes that for just general biosurveillance and general pandemic preparedness. So that would be pretty good. But the whole center feels very black boxy, so I don't have any insight into what they're actually doing. I don't really know anybody from there, so if any of you do, please approach me. So I have no idea what the actual focus will be. It just seems very vague, like integrate information about pandemics. Cool.
One of the longest stages of vaccine development is in the clinical trial, yes. How much of the speed advantage does Alvea's solution gain, and how do you speed up clinical trials?
Yeah, this is a great question. And yeah, like testing the drug clinically and preclinically does take a lot of time. But we actually found a lot of bottlenecks even before this. And so even in getting a simpler vaccine design and making the whole production processes faster, integrating manufacturing capabilities, all of this can already save us a lot of time. Then for clinical and preclinical testing, so there's the approach of platform vaccines using technology that is well established. For example, plasmid DNA, we have known this technology for 3 decades. There are a lot of vaccines that are very similar. Like there's a very similar vaccine to ours, a DNA vaccine targeting COVID, ZyCoV-D. It is already licensed in India, and we're using a pretty similar technology. So we can be very certain that this technology is actually safe. We have a lot of preclinical and clinical data already, and our vaccine has just adapted some of the sequences, the DNA sequences. And so having vaccine platforms where you only make minor changes, but can also already be like pretty certain that the technology is safe, then you could use abbreviated clinical programs. And during the pandemic, we did have abbreviated clinical programs and getting emergency use authorization. So even before phase 3 trials are finished, that you can already start distributing the vaccine. Yeah.
Another question is, within the EA community, biosecurity has become almost synonymous with engineered pandemics. Do you think that we are not putting enough emphasis on other biorisk? For example, non-existential biotech risks subject to value lock-in.
Okay, this is a great question. I may try to answer at first and then you go ahead. The part about value lock-in is very interesting. I want to focus first on that we focus a lot on global catastrophic biological risk, just like the worst possible outcomes, because biosecurity is not necessarily neglected in its totality. So there are a lot of efforts to promote pandemic preparedness, and there is considerable resources put into this. But what is actually neglected is looking into like what happens if we have a pandemic that is worse than COVID. And therefore, as we Jasper mentioned, the scope sensitivity. So we actually just want to focus on the worst possible outcomes.
What Anemone said. I'm also not as worried about value lock-in in the EA community or within the long-termist biosecurity community. People have shown how flexible they are in their thinking and their approaches, and if suddenly GCBRs are solved somehow, but antimicrobial resistance is not, I don't see a reason why one wouldn't pivot then. But yeah, like Anemone said, many of the other approaches and the other non-existential biorisks is just already being worked on. So yeah.
What does Alvea plan to work on after COVID vaccines? How widely applicable are DNA vaccines expected to be?
Okay, about the first question, it's a great question, and unfortunately I can't say anything about this. I can say as much, we are working on other projects in parallel, We're still pursuing our first DNA vaccine, so we are still in phase 1, and we'll see how good the vaccine actually is, and then we'll see the potential of DNA vaccine. We are currently waiting for efficacy data, and based on those data, we'll make the decision on whether or not to pursue this, maybe make changes to the vaccine. So in our production process, we focused a lot of speed. So we took a very simple design. But if we put more thought and effort into this, we might just make minor changes that actually increase efficacy of the vaccine. But yeah, unfortunately, I can't say much more than this. I can say as much that Alvea is not necessarily going to be just a vaccine company or just a DNA vaccine company. Coming from an EA background, it is important to us to pursue the most impactful project. And right now it seemed that DNA vaccines against COVID was a good approach. If it turns out this is not the case, we are quite flexible to consider other approaches.
How fast would we have to respond if the engineered pathogens were particularly optimized for damage?
Yeah, I feel like this already veers into kind of info-hazardy territory if one would, if we want to discuss concrete attack, models or concrete scenarios. But generally, yeah, if one thinks about something like a very broad example, say like airborne HIV, it's very important to both have very good early detection to prevent people from getting infected in the first place, because it might look like something where once you have it, you can't do really much, and it's really important to detect it and then to, say, mask up everybody, or everybody logs in and all the essential workers go into their hazmat suits and, start working on the next DNA vaccine or whatever. So ideally, everything needs to be in place so that as soon as something comes up, which is extremely dangerous, everything can just snap into place. And it's less about how fast do we have to react, but is everything in place so that we can react in the first place, so adequately react in the first place. And in terms of development timelines, yeah, people sometimes speak about the 100-day vaccine, and I think this is just like a very good rough ballpark estimate. If we manage that, that would be pretty great, but we also need to have all the other systems in place.
So would you say that we've got most of the technologies necessary to have an effective response?
No. Yeah, like I said in the overview, early detection is still lacking. There are a lot of open questions. We don't have a great early detection system. We detected COVID, but it wasn't very efficient. And if we would have something which was more sneaky than COVID, then no chance. Same for great PPE. Does everybody have super great N100 masks at home, which absolutely protects you against even the most contagious, say, measles or something? No, we don't. So as long as we don't have that, yeah, no.
Final question. What would you consider to be the low-hanging fruits of this field, both within the fields as well as in general?
I think PPE seems to be relatively low-hanging. It's very concrete, you can work on it, we know how it looks. There are some, of course, governance questions attached to it in terms of distribution and stockpiling and so on, but it's very actionable. So I like it for that reason. Yep.
Yeah, I definitely agree with PPE, and then given my background, I know more about vaccine development, and there's so many inefficiencies in vaccine production, and a lot of those are regulatory aspects. For example, the time it takes for the committee to review your ethics application to conduct a clinical trial. So they meet infrequently, and then they come back with questions, but then you can reply to the questions as fast as possible, but they only meet again in the next month, so you lose another month, just like unnecessary time, and this in a pandemic setting. So there's so many things that would be so easy to change, And yeah, I don't know how low-hanging this is because this is well-established frameworks in which we have to act. But yeah, I think there's a lot of low-hanging fruits to be seen.
Thank you very much. Please, a last round of applause for Jasper and Mona.